hello, welcome. So last time we left off, we actually developed our boundary layer equation for relatively high Prandtl number fluids with what do you call that? Let's see. For the energy equation, sorry. This is our energy equation for high Prandtl number fluids. Of course, the limit x2 here will depend on whether it's a high or low Prandtl number fluid. You can just swap it accordingly. But more or less, the form of the equation, no matter what the assumption is, it will still look like this, except this limit here is changed. Now let's take a look at the let's see. Let's take a look at this other term. What do you call that? Yes. We'll need to take a look at this term here. Okay, so I think some of these steps are a little bit more how do I put this? A little more redundant. So okay, before I take that away, let me uncomment more. I can't remember what I wrote even. Alright. Alright, let's see. Okay, so now we want to deal with this equation over here. We want to deal with this equation over here. Okay. Now we are done with energy equation. Let's move on to momentum. Okay. Okay, so this is the momentum equation which we want to again integrate. Of course, we'll start from the left. All right. Okay, we'll start from the left. Okay, so the left here, we can actually use the same trick we did the last time. Okay, we use the same trick we did the last time, which is again our we did the same trick. Okay, we are doing the same trick. I'm bringing the U in. Okay, I'm bringing the U in here. Then I'll have okay, I think I skipped a step. Yeah, I'm bringing in the U so that I will get del by del x of UV. Okay, del by del x of UV, and I will have minus. Okay, I will have a minus V del U del X. V del U del X. Hope you are following me so far. Okay, so I'm bringing in the U term, and then I'm kind of swapping around. This is just a product rule. Okay, and what do we notice about del U del X here? Del U del X can be we can eliminate U considering the 2D continuity equation. Okay, we can eliminate it using the 2D continuity equation, where let me just copy and paste, and I'll just say this. Okay, del V del Y equals to minus del U del X. Why am I doing that? Because because this term here, once we change it to a del v del y, it is exactly the same as this term. Okay, so that makes life easier for us. You always do things that make life easier. don't make life more difficult for yourself. Life is hard enough as it is. Okay, so we can substitute this back. I think the rest of the stuff I can like don't. Yeah, I'll just delete that. Anything else? Hopefully we'll just run it from scratch. Okay, so I'll substitute back in here. Okay, and I'll get this equation, and after that I'll just combine these. I'll combine this term here with this term here, because v del y and v del y, they are exactly the same terms. Alright, so this one I will just combine here, and of course I can actually just say that d by dy of v square is equals to 2v del y. That's just standard algebraic differentiation. Then what about the first integral? Okay, the first integral will be quite straightforward to evaluate. Okay, we'll just need to evaluate uv at the wall, which is 0, and uv at the free stream, which is also 0. I think that's a typo here. Okay, this should be right. But anyway, either way, it will still drop out to 0. Okay, minus uv wall plus uv u stream. Okay, equals to 0 minus 0, and that's just 0, because free stream, in the free stream we don't have any like so-called significant velocity. Okay, compared with the other terms, of course, this should be very much 0. So the first term drops out. We are left with integrate from 0 to infinity, or x to the free stream area, dx d by dy of v square. Okay, d by dy of v square. Okay, and then we'll need to do a simple Leibniz rule again, by which I hope by now you would know that, I'm going to say, without proving this with the same rigor that I did in the last video, I can just swap around the order of the differential and the integrals. Okay, because of the way we define our limits. Okay, so anyway, I mean, we can do that, but I'm not going to do a second demonstration of the Leibniz rule. It's very tedious. So by Leibniz rule, I'll say without vigorous proof. Or maybe I'll just swap out half the. I'll just do a little bit of a swap. Okay, let's go back up. Okay, so where we did Leibniz rule, I'll copy and paste. Okay. Okay, so maybe it's not that tedious because I did most of the work before. Okay, so again our x and y is swapped around. Okay, our x and y is swapped around. Okay, we'll have the same limits where I have this dp being the boundary layer, or we can use x infinity if you want. The only thing is that f y and x, that's just equals to v square instead of v and t. So since everything is kind of the same, I can just copy and paste vt everywhere. Yeah. Okay, copy and paste vt v square everywhere I see vt. And okay, this term drops out to 0. This term also drops out to 0. Why? Because we are evaluating v square at the boundary layer, at the edge of the boundary layer, which this thing will just drop out to 0 as well. Okay, so hopefully that's enough proof. Okay, I didn't spend that much time because I just copy and paste what we had above and it's all the same. You can use x infinity here for the same reason. It's the same idea. Okay, but long story short, this integral part can be swapped around. So I'll take the fraction partial by partial y outside. And of course, instead of x infinity, I can swap all these limits out for high Prandtl number fluid. I can swap it out for delta p. Not an issue. Okay, so that's one. Okay. So what about this? The second term is quite easy as well. Okay. Since this is all doing with respect to x. Okay, so we will need the wash, sort of the let's see. Okay, so we have new partial v partial x. I would evaluate this at the free stream. Okay, I'll just put delta p here, close enough to free stream. Minus same thing, I would evaluate it at the wall. Okay, I will evaluate it at the wall. Okay, and obviously, obviously this part here in the free stream, there I won't expect very much velocity variation in comparison to the wall shear stress or the wall strain rate. I think this is called the wall strain rate. Okay, so I'll just delete this part because this first term is negligible compared to the second term, which is the wall shear stress. Okay, so substitute that back in. Subs back in, and then I'll just get this term here. Okay, I'll substitute this term back in here, and of course the last term also pretty straightforward. Okay, pretty straightforward. Okay, why do I have a theta? Yeah, is it a theta? I think it should be. Okay, yeah. Yeah, this is a theta. That's right. Okay, so what I just want to do, theta ts minus t infinity equals to t minus t infinity. That's why I actually wanted to use t minus t infinity, sort of to swap over the variables earlier. Okay, for the last term. So yeah, let's evaluate that integral, and then I'll just say it's equal to t minus t infinity g theta here on the outside, or g beta, beta, then I will have this. Everything else should reside on the inside. Okay, substitute back in. Then we will get something sort of our final form. And of course, momentum, the so-called equations, the continuity equation is already implicit inside the momentum and the energy equation. We have actually substituted it in quite a fair number of times. Okay, so now, so you take a look at the momentum equation, the form of the momentum equation. It's like so: d by dy, integrate from 0 to delta p v squared dx, and then you have this viscosity term and then the buoyancy term. Now, if you look at textbook, this is, in Bijon's textbook, this is the final form of the boundary layer equation. He uses the term x to denote, x is a value big enough such that you encounter the free stream. Okay, I like to use delta p in this one just to make it a little less abstract, but if you have liquid metals, then you cannot use delta p to be your outer boundary layer thickness. You have to use it to be your thermal boundary layer thickness. Okay, but this is what this big X here is for. Okay, so X is for an X value big enough where all values T, U, V, Tu and V are in their free stream values. Okay, so that's what I'm saying here. So you integrate across the whole boundary layer, not just the thermal one, but over the momentum one as well, whichever is bigger. Okay, so this actually applies to both. Okay, so remember, you see this part here, that was the energy equation that we just derived last video. Yeah, over here. Yeah. So this is how we derive our energy and our momentum integral boundary layer equations. Now we can start to try and solve. Okay, so now we can start to try and solve this. Okay, again we need to substitute in our velocity profile and temperature profiles, and we'll see what happens. Where's our velocity profile? I think I lost. Yeah, here you go. Page. Wow, 55 pages. My goodness, I've been doing a lot of work. Where is it? How much time do we have left? Okay, no, right on time. So let me just do this. T minus T infinity equals to this form. Okay, this is the temperature profile, and of course the velocity profile is a lot more complicated. I didn't so-called do it rigorously, but it's just an assumed velocity profile. And this will help us to get a rough idea of what our our equations were like. Okay, so reason why we like to swap it into the T minus T infinity is because this is the way we kind of define our velocity profile. I mean temperature profile. Okay. Based of course on the dimensionless temperature, because if you bring this to the other side, it is dimensionless temperature. And of course you have the boundary conditions. What is your heat flux at the wall? And what's your heat flux at the wall? And what is your what is your what do you call that? Oh my goodness. Yeah, what is your shear strain rate at the wall? If not shear stress. Okay, these are your boundary conditions that you need to set. Okay. All right, so this parts, I guess in the coming videos we can actually just substitute all of these in, all of these expressions in, and it will get messy, I can promise you that, but hopefully we can simplify it to something a little more palatable. Okay. So I'll stop for now. I'll see you guys again. Bye bye. Okay, let me finish this.